The last thing that I wanted to do was to talk about a theorem about inner products, which is called the algebraic properties of inner products. To talk about algebraic properties, we're going to need a few vectors. So we're going to need x, y, and z, and we'll call them all column vectors. And then we'll let a and b be scalars. Then we have a few things to be true. The first algebraic property of a inner product is something known as bilinearity. And I like to think about bilinearity as two linearities. One of them is called linearity in left argument. And that means if I take ax plus by and I dot it with z, I guess I should be a little careful here. God, that's cool. Ax plus by dotted with z. Can you guess what's going to happen? Ax dot z plus by dot z. In other words, if I take the inner product in the argument on the right-hand side, I can pass that through vector addition and scalar multiplication, and that's where the little dots make sense, right? This dot right here, scalar multiplication. This dot right here, inner product. This dot right there, yeah, so there's three different multiplications happening on that board in that one sentence, right? Okay, so could you guess if we have linearity in the left argument, what else do we have for bilinearity? Linearity in the right argument, and can you guess what that means? Well, I would have x dot ay plus bz, and could you guess what that must be? B xz. That's called bilinearity. It's linear in the left argument and it's linear in the right argument. Okay? Inner products are also what we called symmetric, or the property is known as symmetry. Could you guess what symmetry means? Yeah, way back when in scalar space you would have called this commutativity. We don't call it commutativity in inner products because it's not all inner products are on scalars. So you can have an inner product between functions, for example. And then another one is called positivity, which means if I take x inner product with itself, do you know it will always be true? That will be positive as long as x is not 0. Could you guess what x dot itself is, or x inner product with itself is, if x is 0? If I multiply 0 by itself a bunch of times and add all the resulting products, what do I get? 0. So x dot itself is 0 when x is the 0 vector.